toi-même parce que je crois que c'est prévu dans ta présentation. Donc,
Effectivement.
voilà, donc tu peux y aller quand tu veux, vas-y.
Ok, super. On en discutait il y a quelques minutes. Si les gens préfèrent que je parle en anglais ou en français, pour moi, c'est un peu plus facile de présenter en anglais pour éviter de parler en franglais quand je devrais décrire des termes plus techniques. J'espère que ça dérange personne. Mais je peux m'introduire en français, évidemment. Donc, je m'appelle Martin Brandenbourger. Et je suis actuellement en post-doctorat. Je travaille à la fois à l'Université libre de Bruxelles et puis à l'Université d'Amsterdam. Et aujourd'hui, je vais vous présenter des travaux donc, qui concernent des transports induits par des asymétries géométriques et des interactions non conservatives dans les systèmes bio-inspirés. Donc, ce travail a été fait en collaboration avec Corentin Coulet, Anania Gatak et Jasper Van Wezel de l'Université d'Amsterdam, et puis Colin Scheimner et Vincenzo Vitelli de Chicago University. And so let's continue in English. So the idea here of this long title is just to try to understand how we can generate fluid flow in specific directions, basically. And here I can show you a very first movie where what you see is a tube in a circular shape. This tube you can deform it, and it contains liquid. And what you can see here by following this bubble is that it looks like there's a flow that is going in one specific direction in this direction here. And so the goal of this talk is simply to describe you all different methods that we've been studied to understand how flows can flow unidirectionally, basically. And before I go into much more details about those kind of experiments, as Susie just said, I wanted to introduce myself a little bit more. So my general interest in physics is to explain the shapes and the transport properties that emerge from the coupling between fluids and soft solids with external fields. And here I'm showing you a few examples. So during my thesis, I've been interested in capillarity and the physics of droplets. So I've been studied, for example, droplets with an excess of electric charges. And what you can see here is that this excess of electric charges, for example, can affect the coalescence between those droplets, of course. So that's one example of the study that we've done in microgravity. I've been interested also in other systems concerning droplets. I've been studied, for example, the Leidenfrost effect, where here it's quite interesting to try to understand so what you have in the Leidenfrost effect is a droplet that is levitating on a vapor layer due to the fact that the interface here is at a high temperature. And then you can study the shape that takes these droplets or the shape that takes this interface here if it's a liquid as well, and study the vapor flow in between the two. And then lately, during my postdocs, I've been more interested into looking into fluid structure interactions, and more so fluid structure interactions inspired by nature, and which means related to this notion of living system and let's say active solids. And that's what I'm going to talk a little bit more about today. And well, first of all, the reason why those systems are inspiring me, well, it's for the following reasons. Basically, I think there's a lot of fundamental physics there is still to understand when you gather together those notions of fluid mechanics, solid mechanics, and this notion of activity of non-conservative forces in those systems. And of course, if you think about living systems, there's a ton of phenomena where those three topics are gathered together and where you have interesting behaviors to observe. So here you can observe, for example, cell locomotions that are moving in specific directions due to those active interactions. But this is not only occurring in biology. For example, in engineering right now, there's a lot of new topics that are being developed concerning smart matter or soft robotics, where those three topics are also gathered together and where we need to better understand what happens once they are interacting with each other. And one of my favorite examples is the soft robot that you can see here. So it looks like an octopus. It's an artificial octopus, where, well, it was one of the first soft robots that was able to move by itself independently of external controls. And the way it goes is that, so we fill people here fill a reservoir with liquid, red and blue. This liquid then flows in a microfluidic, in a series of microfluidic channels that have soft valves that can be opened or closed. And these soft valves, they are basically reorientating those flows towards the leg, such as liquids arrive in one leg after the other, which allows this robot to move. And this liquid goes from a liquid phase to a gaseous phase here to generate the deformations of those legs. So you see that in engineering, people are already capable of realizing quite complex systems, but for a lot of those properties, nature is still a lot better than what we're able to do artificially. And for example, if you want to create liquid flows and transport liquid, there's much more efficient ways than just emptying out a reservoir here with elastomers, pushing on the liquid. And one example is the lymph flow. So here I'm showing you a very first movie where the bright color is the lymph in the arm of someone. And what you see is that this lymph is able to well, go through this channel via pulses, basically. So here you see a pulse of lymph that goes through the lymphatic channel. And the way it works is the following. So let me show you a zoom on one lymphatic channel. That's what you can see here. So here you have two images of the same lymphatic channel. And the way liquid is transported in the system is via the following method. So you have a soft tube that contains the lymph. And what's going to happen is that muscles are going to compress this tube. So if you compress a tube containing liquid, of course, what you're expecting is that the liquid is going to flow in both directions. But what you want is to transport it in one specific direction here. And the way it is done is via, well, I would say two methods. The first one here is the presence of those asymmetric membranes that you can see here, that have a certain orientation that is going to help the liquid to flow in specific directions. And the second method that is used by the lymphatic system is that those compressions of the muscles, they are not completely random, but they are triggered by what is called active feedback loops. And what those active feedback loops do exactly is that, well, it's within the living system, basically, the lymphatic system is able to locally measure certain pressure, transmit that information, and then ask muscles somewhere else to apply a pressure on the system. And what emerges from that is waves of compression that go in one specific direction and over very large distances. Okay. And so what I'm going to tell you about today is how we got inspired by those phenomena to try to better understand the physics that happens in those active systems. And first of all, of course, we wanted to look a bit more about on those deformable membranes. And the approach that I like to have is to develop model experiments, basically. So instead of directly going into looking at the lymphatic system, which is, by the way, something that is very small, and of course that has to be looked in vivo, what we did is to think about what would be the simplest experiments that would capture this phenomenon. Well, here is a very simple model, right? You just have a channel with containing a liquid, and then here you have a membrane that can deform within the flow, for example. Well, that we can easily make in the lab. So what I can show you, for example, here is a schematic of one typical experiment. So in gray, you have this rigid channel within which liquid can flow from here or from there. And then you add those deformable objects here in black, that are going to affect the liquid flow itself. And the idea that we followed here is to use 3D printing techniques to explore how the shape of those deformable objects is going to affect the flow. So it's kind of efficient because you just have to change a few parameters on your 3D model, and then you print those models, and you can perform experiments, basically. So let me show you one typical experiment here. What we have here is a top view of this experiment. And we directly see here why it was interesting to simplify a little bit the lymphatic system, just to look at the physics of what is happening. Because here, well, now we can clearly see the position of those deformable objects. It's easy to track their deformation, to define their initial positions, such as by this angle θ0. And then we can as well very easily measure pressure differences, for example. And so here on those images, you already see a series of observations of the deformation of this object within the flow for different flow rates. And what we already see here is that basically for backward flows or for forward flows, you do not observe the same deformation of the object. So it looks like the asymmetric shape of this object is going to directly influence the way it's deforming within the system. And the hope here is to better understand how this asymmetry affects the deformation of the object and the flow, to understand how it can generate flows in specific directions, for example. So what we can do is to do some measurements. And here I'm just measuring the deflection of this object as a function of the flow rate. And I'm showing you two typical experiments here. So the first one in blue is the very first one that you can maybe do in the lab. So you have your 3D schematic and you ask your 3D printer to print your experiments. You do some experiments at different flow rates and you see no deformation. So what you get from that is that well, this object just has a very high stiffness, higher than what you were expecting. So you redo your series of experiments, but then you ask your 3D printer to print this deformable object with a lower stiffness. And then what you can see here is that, well, this object is deforming in the flow. And as expected, the deformation is asymmetric if you compare forward flows to backward flows. Beyond those deformations, you can, of course, as well measure difference of pressure as a function of this flow rate. And that's what I'm showing here. So here we can first look at the blue experiments. What I have to specify here is that we are working at lower Reynolds here. So of course, if this object is not deforming with the flow, we're expecting that this pressure difference is going linearly with the flow rate. But then as soon as this object is able to deform, what we observe is that we obtain those nonlinearities here that relates the pressure difference to the flow rate. And once again, beyond the fact that this behavior is nonlinear, what is interesting here is that it's really asymmetric. So if you compare to the linear case, you see that for forward flows, the pressure difference is growing at a lower rate than the linear case. But on the opposite, for backward flows, what we observe is that the absolute value of the pressure is growing at much larger rates than the linear case, basically. Okay, so that's the first observation. And of course, we can rationalize what we're observing here. So what we've done is some COMSOL simulations, for example. We just had 2D simulations here. And those 2D simulations were already in good agreement with what we were observing experimentally. So here you see the blue and red squares that corresponds to those COMSOL simulations. And then we wanted to put some physics as well on what we're observing. And so the approach here that we had was to try to develop a model that would be as simple as possible. And what we observed previously is that those deformable objects, even if they deform quite a lot, they do not bend much. So we simply decided to describe those systems as rigid plates that would be connected to a torsion spring on the side of the channel here. Which means that it simplifies the problem quite a bit, because you can really define the deflection as being this angle theta. Here we start with an initial angle θ0. And then if you want to express this deflection as a function of the flow rate, you just have to equilibrate the pressure applied by the flow and the resistance of this torsion spring. And then from there, if you know the position of your object for certain flow rates, you can deduce the pressure that is generated by this flow. So with this simple model, we understand how the flow is forcing this object to deform, and since this object is deforming, it's affecting what is the pressure that you can measure within the channel. But the real goal here that we had was to understand how the shape, the overall shape of this object would affect those kind of nonlinearities. So one way that you can go is to well, develop your model around small flow rates and small deflections to have something purely analytical. And then what you obtain is that the deflection here is going to vary linearly with the flow rate, and the pressure difference can be expressed as going quadratically with the flow rate. And now we have parameters that are going to depend basically on the geometry of your system. Typically, this initial angle θ0, for example. And so what we can do is, for example, look at what we define as the mobility here, which is the ratio between this deflection and the flow rate. And what we observe is that this mobility starts from very low values and then keeps increasing for experiments, simulations, and the model. And what it means can be expected, of course. What you have is a channel when you have those deformable objects. And if θ0 is near 0, well, those objects, they are along the wall, basically. So they are barely interacting with the flow, which means that your mobility is really low. And then as you increase this angle θ0, well, this object is more and more interacting with the flow, and so this mobility is increasing, of course. What is more interesting is to look at this relation between the pressure and the flow rate. And as I was telling you before, what we want to do here is to characterize the asymmetry between forward and backward flows. And well, if we follow this, then the asymmetry is simply expressed by this parameter epsilon here. And if we plot epsilon once again as a function of the initial angle θ0, then we have those results, which are showing that basically it looks like there is an optimum value of this initial angle θ0 to maximize the asymmetry of the flow here. And once again, we can understand that if we think about the physics of the object. If we are at very low values of θ0, well, the object is barely interacting with the flow, so you should have something that is mainly linear, and you have a very small asymmetry. Then this asymmetry is going to increase as the mobility increases. But of course, well, now if you go to very large values of θ0, such as 90 degrees, well, your object is symmetric, right? So the flow forward or the flow backward should have the same behavior, which means that your asymmetry here goes down to 0. And so in between, what you have is maximum. So that's the first observation here, is that if you want to maximize the asymmetry between forward and backward flows, you should choose correctly the initial angle of those deformable objects. You can go further, of course, and for example, look at the overall length of those deformable objects compared to the size of the channel. And you see that, of course, the longer those objects are, the higher this maximum of asymmetry is, basically. Okay, so that's the first step here. I've described how a deformable object could affect those pressure flow relationship. But if I think once again about this lymphatic system, we are still really far away, of course, from that object. And we did, first of all, we did a lot of geometrical simplifications here. So one thing that we can do to go one step further is to, instead of doing this quasi 2D experiment, reproduce the shape of a lymphatic channel. And in order to do that, what you do is that you just go read some physiology papers. Oops. You go read some physiology papers. That's going to wait. And you obtain scans, 3D scans of those lymphatic channels and those lymphatic membranes that are called lymphatic leaflets. And then you can reproduce the shape of those leaflets in your as a 3D schematic. So here you see a 2D cut in this 3D schematic, where you have here part of this deformable membranes within the cylindrical channel. And they are maybe a little bit better to observe here. So this is exactly the same schematic. And what is happening once again here is that, of course, you can define geometrical parameters, right? I can define a typical length A here, or an initial angle θ0 as I was defining it before. And now that we have this 3D object, what we can do is, again, print it and do experiments. So here what I'm going to show you is an experiment that is a little bit different. now we have printed out 2 pairs of those deformable membranes that are connected along a tube. And what we're doing is that we are injecting some liquid flow in between those leaflets. And what we want to do is to measure the outflow on each side of this system and look at what is the influence of those leaflets, of course. So I can show you a typical experiment here where so we generate some inflow and we measure this outflow. And what you observe is that for any inflow, we have a difference in between the outflow from the left side or the outflow from the right side. And this is expected, of course, right? What we have here is that in this case, we have a liquid flowing and going along the direction of those deformable membranes, which means that the outflow here is growing at a slower rate than the linear one. And then in the other case here, we're going against those membrane. And so whoops, that's the opposite. And the outflow can grow at a higher rate. So basically what you can define once again, it's an asymmetry between those 2 outflows. And if you define such asymmetry and you look at different geometrical characteristics, such as this initial angle θ0, what you obtain once again is that you get a maximum. So for a certain value of θ0, you have a maximum of this asymmetry where you have much more liquid going one way than the other way. And that's kind of cool because what it means is that while we observe the same results for this much more complex geometry than for the first case, and it makes us hopeful to then translate that observation to biology by saying, well, maybe if your lymphatic system malfunction is because look at the shape of those membranes, they are really far away from the optimum shape that you would need to generate flow rates. So that's kind of a next step that we are planning to perform here in the following month. And that's a collaboration that has been started with Jean-Paul Belgrado from the Université Libre de Bruxelles, where we're going to compare those real shapes to the models that we've been developed with 3D printing. Okay, so that's a good step. And we can give here maybe a first conclusion, which is, well, with model experiments, models, and simulations, we capture the nonlinearities and the symmetries generated in this pressure flow relationship. And then it looks like we can translate those first observations to much more complex systems, such as the lymphatic leaflets. But of course, there's a lot of things that I have not taken into account so far. If I'm really inspired and if I really want to describe this lymphatic system. And first of all, of course, I was telling you that this channel is compressed by muscles. Well, in the previous experiment that I showed you, I considered stationary flow, but you can understand that it's really not the case in this active system. And one way you can introduce that is, for example, by varying cyclically your flow within your system. And that's the first experiment that I was showing you here at the very beginning of the talk. So we have this tube that is deformable. And here at the bottom, what I didn't tell you is that we can inject and withdraw liquid. And of course, if you inject and withdraw liquid in the system, initially you expect just a symmetric behavior where flow is going to go both ways and then go back both ways in the system. But here in this small part, we have in fact 2 pairs of those deformable objects that are a bit more easy to observe here. And of course, that's exactly what I explained you before. Those objects, they are deforming with the flow, and it's affecting the way the liquid flows. What we can measure is that they are deforming in opposite phases here. And so what it means is that it overall generates circulation in the system. And so you can, for example, track the displacement of the bubble that I was showing you, and you see that it moves at a certain speed. So that's one way of trying to introduce those non-stationary behaviors. But what we think is that there is something much more interesting to be inspired by in those living systems, such as the lymphatic system. And this more inspiring thing is one of the things that I was describing before. It's the fact that apparently this displacement of the lymph by pulses is due to the fact that within the system you have those active feedback loops that are capable of measuring, getting some information somewhere and transmitting it to muscles that are going to apply pressure somewhere else. And this basic phenomena, very local phenomena, leads to an active compression waves that is, well, very impressive because like it goes in one direction and it goes over a very long distance, even if you're in an overdamped system. So, well, what we would like here is to develop a system with some kind of same feedback loops that would allow us to observe those amazing behaviors, of course. And well, what I have to tell you first of all is that, of course, we took the approach of a physicist to look at this. And so the first step is to look at an active solid. So first of all, I'm going to talk here about a purely active solid that is not interacting with a liquid, that does not look like a lymphatic system. And then, of course, what we are developing right now and in the following months and years is to better understand how the fluid structural interactions is going on between this active solid and the liquid phase that we have in our system. So now that I've told you that, here's how our active solid is looking like. So it looks like a circle so far. And let me explain you step by step what we have here. The first thing that you can focus on is this blue part here. So this is just an elastic ring to give some elasticity to our object. So it's going to resist to deformations. Okay. And then below this elastic ring, it looks like we have, let's say, building blocks or unit cells that are looking the same. There's 12 of them in total. And if we look at the side of them, here's how they look like. So very quickly, what we can see is that, well, there's a bunch of electronics maybe, and then there's two arms here. Those two arms, they're in fact connecting one unit cells to its two neighbors, okay? And what is important here is that these two arms, they can move one compared to each other. So if I define an angle theta I here, oops, yeah, if I define an angle theta I here, this angle can easily vary. And so what I have once again is just, let's say, a circle with a certain elasticity defined by this blue part. And then there are some unit cells within the system that are doing nothing so far. Well, the only thing that it can do maybe is that since they are a bit heavy, they could add some friction to your system, of course. But that friction you want to avoid. So to avoid friction, you just have to think a little bit. Maybe go outside and talk with colleagues. And then some ideas can come up. And the idea that we had was just to recreate an hierarchy table in the lab. Okay, so now I can show you how the experiment looks like so far. And it's just a ring with a certain elasticity that we can, for example, send against the wall, and it's going to deform quite typically. So nothing new here. But of course, we didn't spend a lot of time adding those unit cells for nothing. The idea here is to add this notion of feedback loop that we were inspired by. So here's what is composed of one unit cell. It's composed of an angular encoder that is measuring angular positions, this angle theta I that I've defined here. Then there's a microcontroller that is going to receive this information and transmit it. And it's going to transmit it to a DC motor here. And then DC motor can apply a certain torque that is going to be proportional to to the signal it receives. Okay. So what does that mean? Well, it means that if we are now looking at our system here, we can define some feedback loops that are going to add some activity to our object. And let me take the example of one unit cell and zoom in on it right here. So we have one unit cell, and what's going to happen is the following. Well, of course, you have the elasticity that is coming from this rubber band here. And then there's a second layer within the system where this object is going to receive an information of the angular position of its two next neighbor, theta I plus 1 and theta I minus 1. And it's going to apply an additional torque that is directly proportional to those two angular positions times a parameter alpha that is a parameter that we control. We can call the activity. Okay, and basically what is important to observe here is that, of course, it's proportional to those two angular positions, but this one is, there's a plus in front of it, and this one is a minus in front of it. So what it means is that here, through this active feedback loop, we're generating some chirality within the system, where information always tends to propagate in a specific direction. Okay, so now it's time to play with the experiments and to see what those local active feedback loop do on our system. So I can show you once again the case with zero activity, where we just send the object against the wall and it just bounces off. Then we can ask our small unit cells here to add some activity to the system. And I can send the object against the wall, and here's what happens. The object is bouncing with a certain angle. We can check that it's not due just to some random behavior in the system by, for example, changing the sign of the activity. That's the movie on the right. And what we see then is that if we change the sign of the activity, the object bounces exactly the same way, but with the opposite angle in this case. So first of all, to try to understand what just happened there, we can look at the center of mass and how it behaves. And of course, we can do a lot of experiments with different, let's say, impact conditions. So I can impact my wall with different initial speeds. I can impact my wall with different impact angles. So my first impact angle that I showed you here was equal to 0, but then it could also be equal to 45 degrees, for example. And what happens if we do that is that we observe that, well, really this deflection that we are observing is at the first order, depending on the activity and not on those parameters. So it means that this activity here within the system is controlling how the impact is going to behave, basically. Beyond this deflection, you can also measure, for example, the bouncing coefficient of your object. And what we see here is quite interesting because, well, at zero activity, what you observe is just that there's a lot of dissipation within the system. This bouncing coefficient is at 0.5, which means that you come in with a certain speed v1, and you go out with a speed that is half of this initial speed. But then, as you increase the activity, you increase this bouncing coefficient, and you can even reach values of these bouncing coefficients that are higher than 1. So now your object is bouncing with a speed that is higher than the speed it was coming in. Okay, so that's the first overall observation, but it's quite, well, it's just describing an active impact, basically. But what about the active solid itself? Is there interesting behavior within the active solids that we want to look at? Well, to check that, I can show you some image sequence of our system here. So we're going over time over there. You see that the object coming, it impacts. And just to tell you things quickly, the chirality that we induce in the system forces the system to deform in an asymmetric way. That's what is creating those deflections. But there is much more than that here, because as the object bounces away from the wall, there's something that we can observe if we look at the maximum of deflection, of deformation here of our object. So the green and the yellow arrows. If we follow those green and yellow arrows, you see that basically they're moving along our circle here. So for example, if you look at this red cable here, well, this green arrow is going away from this red cable over time. So what it means is that there's some kind of a wave here that is propagating within the system as you deform it. And one way to quantify this wave is to generate those contour plots. So here on the y-axis, you have the time increases in this direction. And here I've plotted the unit cell number. So we have 12 unit cells here, but in order for the graph to be easier to read, I've just put it two of the same measurements, one next to each other, okay? So we have 12 unit cells, and then I'm showing the same measurements again. And then the color here describes the velocity at which our angle is changing for one unit cell. So what do we observe on this graph? Well, you send the object before impact, and of course the object is not really deforming. Then it impacts the wall, and you see that you generate a deformation within the object. But in this case, the system is passive. So then you bounce away from the wall and not much happens anymore. If the system is active, then you have a much more different behavior here. And that's what you can see here. The object is coming in, it impacts the wall, and then it looks like there's a wave that is starting to go through the system, a wave that is going in the left direction and a wave that is going in the right direction. And well, what is interesting here is that this wave that is going in the left direction has a much smaller amplitude, and it looks like it's basically destroyed by the one going in the right direction. So what it means is that it looks like within this active system, once you deform it, you excite it, you're able to generate a wave that goes mainly in one direction with a large amplitude, even if there is a lot of dissipation within your system. And if I would have continued this measurements here, you could have seen this wave going on and on and on within the system. So that's kind of exciting because now, well, we've used those feedback loops and it looks like we have a behavior that is at least similar as the one that we were inspired with, which is the lymphatic system. In fact, we can go a step further here in understanding the physics of this wave. We've done a series of other experiments with other mechanical systems. And here I can show you one of them where we are using the same kind of unit cells and the same kind of feedback loops. But here the configuration looks more like coupled oscillators, if you wish. And what we can do with those coupled oscillators is look at how pulses propagates through them. So we've defined the same kind of active interaction, and here's what we observe. If we generate a pulse from the left side here, this pulse is going through the wall material. But on the opposite, if we generate a pulse from the right side of the system now, you see that this pulse is going barely through 2 or 3 unit cells. And if you do fine measurements and you measure, for example, the maximum amplitude of this pulse, what you observe is that, well, from the right side, you generate the pulse and then it very quickly dies out. And from the left side, you generate this pulse and then is going through the wall material indeed, but it's also apparently keeps increasing in amplitude as it propagates. And so what it means is that it looks like using those feedback loops is really the source of the emergence of those specific waves that unidirectionally propagates and apparently are able to self-amplify as it propagates in mechanical systems. And what is also very exciting about this observation is that, in fact, that's something that you do not only observe in active solids, but it's a thing that you observe in a lot of active systems. And this phenomenon that I'm describing to you here is what is called the non-emission skin effect. So what happened in the non-emission skin effect is that you have an active system where you tend to localize the vibration mode on one side of your active system. And that's something that has been observed in electronics, for example, or in optical systems as well. So that's the nice thing about it here is that from a first observation on active solids of those vibrational behaviors, it looks like there's a much more fundamental physics that emerges from there. But of course, so far I've only shown you one ring that is bouncing on the wall, right? So we're still far away from describing maybe perfectly what would be an active solid, first of all. And one step to go further is to just add more unit cells. So instead of looking at a ring made of 12 unit cells, what you can do is I'll make 118 of them and then create a whole 2D structures that is interacting exactly in the same way. And if you do that, well, first of all, of course, you can do impact experiments where now your impactor is passive and your wall is active. And well, for no activity, you see a classical impact, I would say. And then as soon as you turn on activity, what you obtain is a behavior that's much more different where I can play it again. This wall is deforming in an asymmetric manner. And one of the consequences of that is that, of course, this object is bouncing with a certain deflection here that you can compare from the active and from the passive and the active case on this on the end of the movie here. And we really see that the activity within the system is directly affecting how dynamically the active solid is deforming here. And of course, in those active solids, you once again observe the emergence of those unidirectional waves. I can show it to you by just poking our object. And if I poke the object with my hands, here's what I'm observing. You see that I generate a wave that preferentially propagates this way rather than in this direction. I can show it again. Here I come in and poke the system. You see that the deformation goes rather this way than in the opposite direction. So what it means is that what we are doing currently is just to explain our experimental observation of these active solids with some theoretical approach, and that's where we are collaborating here with Colin Chandler and Vincenzo Vitelli, who have developed quite recently a very nice approach to describe those active elasticity that they call odd elasticity. And so far, it looks like the use of those local feedback loops that we had in our system is leads to properties that are quite similar to what is expected to observe in those with this approach of odd elasticity. And of course, that's only a first step. And I think we're going to be able quite quickly to describe the new mechanical properties of those active solids with this approach. But what is very exciting, I think, is to then understand how those active solids are interacting with their environment, of course. And so the next step that we are starting to put in place here is to, for example, study how fluid structure interaction, how very specific fluid structure interactions can emerge from those interactions between active solids and liquid flows. And of course, you have already a bunch of very interesting works done on the system, such as the work done on Fusarium polycephalum, where what people are doing is to look at what the fluid flows that emerge in very complex networks that are made of a living system, so an active solid basically, that is able to reorientate those flows as a function of different excitations and so on. But beyond that, of course, what I think is really exciting here as well is that we're not only reliant on living system anymore to observe those active behaviors, but we can develop our own model experiments where we can use well, the notion of active metamaterials that I was showing you before, but also the notion of active polymers, for example, to create those complex networks interacting with active solids and try to describe the physics of this active poroelasticity that emerge within the systems. And so with that, I'd like to conclude this talk. Here, during the past few slides, I've been describing how asymmetries in shape, but also asymmetries generated by the activity itself is able to generate transport and dynamical deformations. And of course, one of the main inspiration that I had was this lymphatic system that we are still far away from perfectly understanding. And one big step forward that we did is to better describe via model experiments how active solid would behave. And the goal here in the future is really to combine now those two realms to study how active elasticity can affect, for example, fluid transport. And I can show you here a movie of some publications that are already, well, some papers that's already out, where people really use those notion of active polymers, such as photosensitive polymers, to create propagating waves and within in mind to generate those liquid flows on those locomotions, for example. So with that, I would like to thank you for your attention, and I hope you have some questions.